So we were talking about chemical formulas and how the subscript after the symbol for the element tells us how many of each there are. Some formulas, some chemicals have groups of atoms that act as a unit, and they're called polyatomic ions. So polyatomic, poly meaning many, atomic referring to atoms. So these are ions that have many atoms, but they act like a single unit. So it's a little bit like you were playing with Lego blocks, but this particular group, somebody had put super glue on them. You can't take them apart real easily. They just act like a unit, and you kind of have to just deal with it. So if we have two or more of the same kind of polyatomic ion present, we need to use parentheses. And so here's an illustration from your book. Here's this formula, Mg, and then there's parentheses around the NO3, and then a 2 on the outside. If we're reading this, we'd say MgNO3 2. The parentheses here tell us that we have a nitrate ion unit, okay? And outside the parentheses, that tells us how many of those units we have. This is a little bit like shopping at Costco. You can't buy one bottle of ketchup at Costco. There are two, and they're shrink wrapped together, right? So this is like the bundle pack, the NO3. They are shrink wrapped together, and the shrink wrap is the parentheses. Outside, it's telling you how many bundles do you have. Okay, so why do we have to mess around with this? Because if we didn't, if we wrote it, I got a new stylus and I'm not sure that I like it yet. If we wrote it like that, it would be very easy to think that that's 1 magnesium, 1 nitrogen, and 32 oxygens. And that's not at all what we mean. Okay, so this is what we've come up with. We put parentheses around that and use a subscript on the outside to say how many. Now, we don't, you might say, well, why not just, do the multiplying here? Why not just say N2O6? Well, this may become more reasonable to you a little bit later on, but NO3 is an ion that sticks together. And so there is no N2O6 ion. What this compound has in it is for every 1 magnesium ion, there are 2 nitrate ions. So let's see if we understand this. So here's a formula, K2SO4, and we're asked to determine the number of each type of atom in the following formulas. So basically we need a list of the different elements and how many of each atom. So in K2SO4, there are 3 different types of atoms, right? There's potassium, there's sulfur, and there's oxygen. How many potassium atoms are in that formula? 2. There's 2 of those. How many sulfurs? Just 1. And how many oxygens? 4 or 1? 4. Okay, now this one's a little more complicated. Al2SO4 3. So again, we have 3 different elements. We've got aluminum, we've got sulfur, and we've got oxygen. How many aluminums? 2. How many oxygens? I'm sorry, not oxygen, sulfurs. 3. I messed you up. I didn't mean to do that. And how many oxygens? 12. Okay? Everybody cool with that? There are different types of chemical formulas, and we use them in different situations. An empirical formula just gives us the relative numbers of atoms. Empirical means derived from experiment. So this just gives us relative numbers. A molecular formula gives us the actual number of atoms in a molecule of that compound. And then a structural formula gives us more information. It gives us an idea of how the atoms are actually connected to each other. So let's look at examples. Not just yet, though. We often use models. Atoms and ions and molecules are far too small for us to see. And yet it's helpful to have a picture. I'm a very visual person. I need to see it. And if I can't actually see it, I'm going to invent a picture in my mind so that I can see it. Models help us to visualize things that we can't see. So molecular models represent the molecules. A common one is called a ball and stick model. And we actually have some model kits that we'll be playing with in lab where it's almost like chemistry tinker toys. The atoms are represented as balls, and then we have sticks that are the bonds that hold them together. And then you can have a space-filling model. This gives us a better concept of the actual shape of the molecule, but it's a little harder to see how things are connected because it ends up being kind of chunky and we can't really see what's going on. There is a common color scheme that we use. You do not need to memorize this, but we tend to use white to represent hydrogen, black for carbon, red for oxygen, and your book has been using that all the way through. So let's look at one specific compound. This is methane. Its chemical formula is CH4. So this tells us for every one carbon there are 4 hydrogens. So the molecular formula would just be the list of the elements and the subscripts telling how many of each. This is a molecular formula. I'll talk about that later. This would be the ball and stick model. Here black is the carbon atom, and the 4 hydrogens are all attached to the black carbon atom. Now, are there other ways that you could put 5 spheres together? Yeah, there are other ways. But we know from various forms of evidence that this is how the methane molecule is put together. This is a structural formula, not a model, but a formula. It's similar to this, except that it's showing how these are connected. So it's kind of like a flattened version of the ball and stick model. And then this is a space-filling model. If we were able to see a methane molecule, that's probably more what it would look like, because the atoms actually get very close and they kind of merge into each other. They're not separated by actual sticks. So the different formulas and models help us to visualize this world of atoms and molecules that we can't see. Sometimes we'll refer to the macroscopic view. A macroscopic is just things that you can see with your eyes. So, your hands, even dust in the air, you can see with your eyes, but it's not things that you would need a microscope to look at. A microscopic or a particulate view is looking at the atomic and molecular world. So this is the individual particles. We can't see these even with a microscope. So the macroscopic might be, you look at this glass of water. But the chemist thinks a lot on the molecular level. What are the particles doing? What are the particles like in the water? And then we have a symbolic view, and the symbolic here would be the H2O. That's giving us a symbol of what the particles are.